welcome everyone back to The Blind Spot. I am Evan Thompson. I am in Vancouver, and I am joined by Marcelo Gleiser in Tuscany and Adam Frank in Rochester. And today we are continuing our discussion of time. And I think where we left off last time was with the difference between the lived experience of time, the feeling of there being a special moment that is the now, and the feeling of flow and duration, and how that contrasts with time in physics, which is what a clock measures. And I think where we wanted to begin today was with the problems of the direction of time, the arrow of time, and thermodynamics. So that's an issue that one of the two of you, physicists, needs to speak to. So maybe we should begin with Marcelo on thermodynamics and the arrow of time.
Okay, so we're doing a little bit of a history of time here, at least the conception of time in the West mostly, for the last few thousand years. And that's where we kind of left off. The last episode was really the transition between the 19th and the 20th century when Einstein comes in. But we cannot go on without mentioning what happened in the third pillar of classical physics of the 19th century. So you had mechanics, you had electromagnetism, so electricity, magnetism, light, etc. But we also had the study of heat, right, which is a big player. In fact, in our book, The Blind Spot, we start discussing that. And one of the things about heat is that, as you know, and we're talking about the Mertonians last episode, how they, and Adam, I didn't even know this, but you mentioned that they were heating up metal bars and counting the time, how long it takes for this heat to propagate from one side to the other. Is that right?
Well, it was the beginning of the graphing, right? They figured out how to graph the amount of heat in a bar, like how the bar cooled down as a function of distance from the. So that was really, they had like heat or temperature or heat on the vertical axis, and then distance along the. So they were thinking about heat as well.
But I remember you must remember this when we were physics students, like in junior year or something like that. We were calculating the heat diffusion equation, right, which was a partial differential equation that does exactly that, right? That tells you how heat and how the material interferes with the propagation of heat, right? And so what happened with the study of heat was really amazing, and it's a super long story. I won't go through the whole thing, but it was really coming mostly from engineering questions because it had to do with the steam engine, right? And you had Sadi Carnot in particular in France that made this really cool analogy between heat and a water mill. Basically, he said that if you want to move a water mill, you have to have water falling down so that gravity is doing the work to make the wheel turn down, right? So the water is coming, let me see here. Here I am. The water is coming down, hitting the pedals of the windmill or something like that, right? So the water mill in this case, and it's doing work. And so the question then is, the higher the water is, the more it's going to fall, the higher its speed, and eventually it's going to make the wheel work better. So Carnot was thinking that way and said, this is interesting because if you have steam, right, moving pedals instead of water, right, how can you optimize that in such a way that my steam engine, which was all the rave, right, talking about 1820s here, in Europe, would be more efficient, meaning do more work with less fuel. That's the idea, right? Because they're burning coal to make it work. And he realized that a few things doing that, and he was not the only one, but he realized that things which are kind of obvious, but not that obvious, like, heat only goes from hot to cold. And you can never have something, that is cold heat up by itself. You have to have it going the other way. And that's why, when you make a cup of coffee and it's hot, it's going to cool off by itself, right? And that takes time. And so there was this thinking about what's going on there. And the other thing that came up during this time is that when you're heating something up, even if you had a 100% efficient engine, which you never do, there is always going to be some loss, right? That you cannot have a perfect engine. And that means that if you have a system, and correct me here or give me more analogy, a closed system. What's a closed system? That's important. It's a system that cannot exchange heat with the outside. So like a perfectly insulated room, what's happening in there, right? So if you have stuff happening in this room, so let's make it even more precise. If you have like a box and you have steam in one side of the box, right, and cold air on the other side of the box, there's a partition right in the middle, right? And if you remove the partition, what's going to happen is that the steam is going to hit the colder air, and eventually it's going to hit a sort of average temperature between the hot temperature of the steam and the colder temperature of the hot air, right? So that's what we see. What really happened, which was remarkable, and James Clerk Maxwell, who the same guy who did electromagnetism, was a very important.
Amazing that Maxwell actually was one of the players who was known for electromagnetism, also was a huge player in this idea of thermodynamics and statistical mechanics, transferring the idea of what's happening with continuous stuff like, steam, thinking about it in terms of atoms and their motion.
So they went, this is really cool because atoms were not accepted at the time yet, but they use an atomistic way of thinking about, and that what is steam really? Well, it's made of little balls, balls of water molecules, right? And they are moving around sort of randomly. And most of steam is empty space because these molecules are very small. And the guy that actually came up with this was Daniel Bernoulli, a Swiss prodigy dude that had this idea. And so that they started to use this microscopic approach to describe the behavior of matter. So this is really a fundamental, I think, and I think we have to highlight this transition in the way of thinking, that, look, if I want to understand microscopic behavior like temperature, I have to look at the components that make up that whatever the gas is and stuff like that. So Maxwell did that, and he realized that temperature, what we call temperature, can actually be directly associated with the average square velocity of those particles of that gas.
Can I just jump in just because before we get into atoms, just the idea is that, right, so there's classical thermodynamics, which is just people, and what's really amazing about classical thermodynamics and how important it was, because this is going to be foundational for our understanding of time, because things like entropy are going to come out of this, but that it was an engineering discipline, right? This was not theoretical physicists. This was not Isaac Newton sitting in his study pondering the mysteries of the universe. These were guys like with wrenches trying to build machines that would, win industrial empires. But the important thing I just want to note is that even in classical thermodynamics, before we got to atoms, there was already the recognition that somehow there was the connection between the flow of heat, the one-way flow of heat, and time, right? That there was a direction, because I think what we're headed here is we're trying to get towards the direction of time. That time doesn't, unlike space, right? With space, as we talked about last time, you can go forward, you can go back. In time, you can only go one direction. And that direction is actually defined thermodynamically is things go from, hot and then they cool down. They never spontaneously heat back up again. So I think that's just an important point for us to make this already before we even got to atoms. There was this idea that you could connect or you could link the flow of time to the flow of heat. There was a thermodynamic arrow of time. And part of this also, just you've already mentioned it, is entropy, that when you try and use heat to do work, heat is a form of energy. It's random motions that now we know, think of it as random motions of atoms. But when you try and do work, you always have to generate some crap. There's always waste that happens. And so entropy, the increase, whenever you do anything, whenever there's any kind of transformation, you're using heat to do work, this thing called the entropy, which was a new physical quantity, increases in time. And so that was one of the fundamental laws, the second law of thermodynamics, that when there are these kinds of transformations happening, energy transformations, either the entropy changes zero or it goes up.
Right. So back to the little box with the hot and cold molecules, right? It's awesome that you mentioned that, because the thing that we teach in the classroom for everyone is that what you see is that you go from the hot molecules hit the cold molecules, and the cold molecules move a little faster, but the hot molecules move a little slower, and eventually are moving at roughly the same average speed. And if you made a movie of this, right, that the hot molecules hit the cold molecules and then everybody's moving more or less at the same speed. If you play the movie backwards, meaning you have an average, a gas with an average temperature, everybody's moving at about the same speed roughly, they will never go back to the initial condition, which is half of the molecules, the hot ones, were on one side of the box, the cold ones on the other side of the box. So that is an example of the arrow of time. And there is something profoundly, mysterious and natural about that, because our experience of the world is completely based on that, right? So for example, if you're drinking coffee, right, that's the other typical example, and you put cream in the coffee, right? And you mix it. So, you have your cappuccino, since I'm here in Italy, I can mention that, and you get this little combination of stuff, right? The coffee never unmixes itself. It never goes back. So once you get scrambled, you cannot unscramble. In fact, eggs are also a great example of that. When you cook an egg, you have this beautiful little egg, right? And it's all nice. And then you scramble it. There's no way it's going to go back to its original egg. So there is an arrow of time that has to do with the complexity of the system.
Yeah. So that was, so the important part here is that from the physics, but this is before we get to relativity, right? There was already a recognition that time and its direction was related to these random motions of atoms. And the interesting thing here that we can come back to maybe in an entirely other chapter of this, or another podcast, is the equations of motion. The equations that Newton came up that describe these atoms individually are reversible. If I showed you a movie of two billiard balls, two pool balls hitting each other, I can play it forward or backward. You wouldn't know the difference which way it was. And yet you get enough of these things together, and there clearly is a difference between the forward and backward. And this is going to be one of the profound mysteries that physics still, in some sense, doesn't really fully grasp, right? Because we can go in. One of the things that happened was once we had atoms, then there were people like Boltzmann and Gibbs and Maxwell was part of this too, trying to figure out, okay, how can I take these reversible equations for individual atoms and then write down probabilistic equations for them? This is what's called statistical mechanics. And then out of that, get a flow of time. And this is what's called the famous Boltzmann's, the H theorem. He supposedly was able to show that, if you had enough atoms, then probabilistically you could show that in general, they would, that entropy you could show that entropy would increase. But there's some problems in what's called molecular chaos. You have to make certain assumptions about, there's no, what we call correlations. There's no memory in some sense of previous states. But anyway, I think the important point for us is that by the beginning of the 19th century, there's this well-developed or developing statistical mechanics, which sees the arrow of time in terms of, as Marcelo was saying, complexity. When you get lots of stuff together, you get different kinds of behavior than just individual atoms, which you can't tell which direction they're moving in time.
So let me just press on this a little bit and ask you a question from the perspective of statistical mechanics and molecular motion and entropy. Is it the case that it's impossible for things to become unscrambled, or is it just statistically highly, highly improbable? Because of course our experiential sense of the arrow of time, or the inevitable sort of forward movement and march from birth to death, is that it's impossible to reverse that. But in terms of the statistics that are governing that are describing the molecular behavior, is it a question of impossibility or just high degree of unlikeliness or unlikelihood?
The quick answer to that is that it is not impossible. It's just so extremely unlikely that it just basically in practice never happens, right? But if you have an infinite number of universes, which I hate to say that construct that, but if we did, there'll be a universe where things would go back. So what Boltzmann said is that he created, as Adam mentioned, this probabilistic description that has to do with the states of the system. So every system made of a bunch of little particles has many, many possible states, where the particles can be in terms of energy and position, etc. And there is one configuration, one out of gazillions. Imagine how many configurations these particles can have. There is one that is the initial state where things were organized in the beginning. And it's one in a gazillion. There's no, you're talking about more than 10 to the 24th, right? I mean, it's much more than Avogadro's number. You can't rule it out, but, and that's why we don't see it happening. So that was a very effective argument, but there are criticisms, as Adam was mentioning, with assumptions that go in there. And so if you want to be really critical, I don't know if you agree with me or not, Adam, is that we haven't really figured out exactly using statistical mechanics and what we know of particle physics to understand why time goes forward.
Yeah, I remember when I was a graduate student and taking stat mech. And I remember it was David Thewlis, who was, I don't know if David ever won the Nobel Prize, but I think he won the, maybe it was the Fields Medal. I forgot which, but, actually, I think he did actually eventually win the Nobel Prize. He was an incredible condensed matter physicist. And I remember him bringing up what was called the molecular chaos, that there's actually, as you run through the argument, right, of going from atoms with their reversible, individual atoms have reversible equations. Time doesn't, time is just a parameter. You can run it forward, you can backward, doesn't matter. To then when you collect them, when you get large collections of them, that's what this equation, when you do the Boltzmann's H theorem, what you have to do, you assemble a lot of them and you run through the probabilities. And then you have to, sort of set up the argument about their collisions. Thewlis introduced this idea of molecular chaos, that there's an assumption you got to make right in the middle there about how whether these collisions impart any long range correlations, whether it's kind of like in some sense a memory, and you have to kind of erase that, or else the equation, or else it doesn't work. And he made a big point about this. He's like, there's been problems with this forever, and so I would say Boltzmann's H theorem is a beautiful piece of mathematics, and it points in a certain direction. But, with the Lohr-Schmitz paradoxes, people for a long time have been bothered by certain aspects of it. So I would say that it's not 100% clear. The arguments about probability and that there's overwhelmingly likely, with entropy, overwhelmingly likely you're going to end up in these other states that are sort of, time moving forward states. That's very solid. But on the other hand, to get there, there are problems that have sort of, which for us from the blind spot is very much about this not mistaking abstraction for reality. These are abstractions which are super useful, but if you're going to use them to replace the lived experience of time, then you got to be really careful.
Yeah, so that, I think is something worth pressing on, because if the equations that govern or describe the motion of the individual molecules are time reversible, but from the perspective of the large-scale behavior, there's a directionality, then it would seem that one would be very tempted to say something like, well, the directionality is a coarse-grained way of looking at things, and at the fundamental level, there really isn't directionality. It's some kind of an appearance that gets generated macroscopically. And that would be, from our perspective, caught in a blind spot way of thinking, because you're taking one kind of description and privileging it over another kind of description, and they both have their own validity in terms of the context in which they're working. And moreover, the large scale description, it seems to me, at least as a philosopher, doesn't really actually capture the fundamental issue about the arrow of time as we experience it. Because if it's a case that is just highly unlikely, well then, to invoke the multiple universes idea, then, at least it's logically or metaphysically possible that there's a universe in which, I go backwards, and move from being, an adult in my 60s back into the womb. And there seems something profoundly wrong about that experientially and also biologically. It seems that biological phenomena have a kind of time that has to do with their metabolism and their generativity and their development that isn't a matter of statistical probability in that way.
Yeah.
These are really deep conundrums, I think, that get glossed over in a lot of discussions. And that's, of course, what we're trying to bring out and bring to light.
Absolutely. It's behind this whole confusion, behind this whole statistical physics, we have to remember that it all started with an idealization of what's called elastic collisions, or the ideal gas. Right. And so if you want to get a little deeper into this story, right, is that in order for Maxwell to construct his theory, he assumed quite reasonably that those collisions between these molecules did not dissipate any energy, right? They were elastic. So they go boom, boom, no loss of any energy, right? But of course, we know that molecules are complicated things. They have more than two or more atoms and electrons, and they radiate, and when they collide in many ways, unless very low energy. And so the very assumption that you have to have these ideal collisions in order to describe how temperature is really proportional to the square of the velocity, which is what they came up with, are excellent. They're phenomenal descriptions of what's going on. And that's why thermodynamics is such a powerful theory. But they are the map, going back to that story of the map of the territory, right? That deep down, it's much more complicated than that. So when you go from these simple Newtonian time reversible equations to the equations that start to incorporate some of the complexity of those interactions, collisions between them, you go from a second order in time equation, so squared, so if you take t to minus t, it doesn't matter, to a first order in time equation, which it does matter. So you start getting into dissipative systems, which are systems where there's no question that time is going forward. So a lot of the condensed matter physics is about dissipative. So it has first order equations in time. And a lot of the fundamental particle physics and Newtonian physics are usually second order in time.
Yeah. And that, because it speaks, let's just touch on it though for a second, because we're, again, Marcelo and I are physicists. We've all, when I was learning stat mech, it blew my mind. The idea of phase space, which is really where the space of all possible states of the system was one. And if there are 1,000 particles, there are 6 times 1,000 dimensions to this phase space. One of the most beautiful ideas, abstractions in physics, and there's so much power that in it. So, I don't want anyone to be thinking like we're dissing the physics. What we're saying is that there are assumptions and idealizations made in the physics, and this is that you have to be careful about saying that's more fundamental than life, than the experience of life. That is the whole premise of the blind spot. What happens is that people, we develop these idealizations, like the time irreversible equations that Newton came up with, which were originally that they worked best for celestial mechanics, planets going around the sun, which is the most non-dissipative system. It's the one system where dissipation hardly, you don't have to think about it at all. Though even there you really do in long term. But those equations, those are abstractions and idealizations, potent, powerful, and they need an account of why they work. But what you do not want to do is now have to say, oh, now I've got to explain why experience time is an illusion. The time that is most intimate to me, that's not real. I've got to somehow recover that from these idealized equations that don't have dissipation in them. That's really where we're coming from and trying to sketch out a new way, a new kind of relationship between the most fundamental ideas in science and lived experience.
Yeah, and that's worth like making even as a more general point, which is, to put it in philosophy of science terms, that science works with models, and models are inherently simplifying. Models work with simplifications. They abstract, they idealize, and that's what makes them incredibly useful and incredibly powerful. But it's a confusion to then turn around and say that the model has a fundamental status, whereas the experience that's in the background for the model builder is somehow derivative from the model. It simply doesn't make sense. And so our book is a constant effort of reminding the reader, reminding ourselves that this is the situation across physics and biology and cognitive science, and take your pick.
Yeah, and you end up with if you don't recognize that what is fundamental is experience. You have to have already this weird given thing that is to be in the world, to be experiencing. And you want to push that off and then have the equations as being these abstractions being the fundamental thing. Then you end up with all these paradoxes that you got to go through this incredible mental yoga to try and undo. Like, how do I get the flow of time from these equations? It's like, well, it may be that those equations are idealizations and the flow of time is not fun. The flow of time that we experience is fundamentally not in there because they're idealization.
Before we leave this, because you brought up biology, right? And so when you get into biology, then we're so far removed from these simplifications of models that we use in physics that it's incredibly difficult to kind of carry these ideas on into biological systems. First of all, they are open systems. They're open thermodynamic systems, meaning all the laws that we talk about in thermodynamics are not for systems that can exchange energy with the environment, and that's essentially what life does. So for life, to keep because of entropy, the idea that you have decay in time of every organized system, for us to keep looking kind of the same, more or less. I mean, when you look at yourself in the mirror 20 years now and 20 years ago, like, it's not really. But in order to get approximately the same exactly, you have
My beard wasn't always white.
Exactly, right? And I had more hair than this. But the point is that we need to bring in energy all the time. That's why we eat, and that's how we metabolize. And so it becomes a much more complicated conversation, which we'll have eventually. But right now we're sticking to the physics. I just wanted to flag that.
Yeah, that's great.
Since you did, I want to flag one more thing that we'll circle back to when we eventually talk about life, and that is, in classical physics, the default state, if you will, is inertial motion, and then changes are due to outside forces acting on the system or the body. But the default state in an organism is not like that at all. The default state in an organism is constant change, because you have metabolism, you have cell division, you have genes turning on and off, and figuring out, models for that and mathematics for that is extremely challenging and different from what one would be used to if one was looking at it through the lenses of classical physics. Relativity theory is our next destination. So who wants to take the lead of the two of you on relativity?
So just in terms of there's two kinds of relativity, special and general relativity. And the main idea that you want to recognize here, at least in terms of the change from classical to, because we could spend a half an hour just talking about relativity, is and how Einstein developed it. But the important thing really is so first there was special relativity, which was the recognition that there was no privileged frame of reference, right? To describe motion, you always have to write down equations. Those equations always have some frame of reference. There's always I'm 10 units from from that building over there, 10 miles from that building or whatever. And the special relativity did away with that idea and said that really all that matters is, every frame, there's no privileged frame of reference, and that because of that, there's no intervals of time and intervals of space are relative as well. What for one person may seem like 20 minutes could be 1 minute for another observer. Okay, and that was a really radical idea. Unlike Newton, time did not flow universally through the universe. So that's the radical thing, number one, is that time and space are relative to the observer, to the individual observer, and their frame of reference that they're carrying with them as they move around. General relativity generalized that to include gravity, systems with gravity. And then what happened there is that Einstein replaced forces of gravity with actually this idea that it's the fabric of space and time. Space and time actually are kind of a stuff that has a shape, and it's that shape which determines your local flow of time. First of all, it determines how much gravity is going to be experienced by an object, but more than that, it's also the local flow of space and time depends on where you are in that curvy space-time metric, as we call it. And I'm just accelerating through all this to get to one of the most important things that came out of this view was something called the block universe. There was this idea that, with general relativity, you can now think of all space and time, every event and every location as one giant holistic thing, so that your entire life is what's called a world line through space and time. You're born at some point, some location in space and time, and then you sort of make this line through this block universe of space and time. And when you die, it's over. So in some sense, from the block universe point of view, next Tuesday already exists. And I remember when I first learned that, I thought that was the most radical, beautiful, amazing thing. But now I think all three of us have come to the conclusion that the block universe, it gets used in this way where it's treated as being more real, right? Again, next Tuesday already exists, than actually our experience of the future being open-ended.
Special relativity had to do with motions at constant velocity, right? There was always, so it's really about a guy standing at a station, and then another one is in the train moving by at a constant speed. And Einstein used a lot of trains because he lived literally in front of the train station at Bern in Switzerland. It's and Swiss trains, like precision, blah, blah. But what he realized is that if both of these guys, the guy standing and the guy on the train, hold clocks, right? They're all the same exact clocks. They tick and they tack exactly in the same way. And if I am the guy standing and Adam is the guy moving by, if I look at my clock, moving by in the train, if I look at my clock standing still, and if on the earth, and if he's moving on the train but he looks at his clock, we're going to see the same time. But if I look at Adam's clock, which is moving with respect to me, I will see a time which is different from the one that I have in my hand. So moving clocks tick slower. In this case, it happens to be this, and that means that time dilates, right? So that was his insight. And then he does the same thing without just a clock, but with a stick. And then he says, oh, look at that, Adam's stick is moving with respect to me, and it's going to be shorter than the one I have, even though at rest, when we started, we both had a 1 meter stick, exactly, right? So motion shrinks space and slows down time, if you're seeing something like that happening, which was 1905. I mean, the guy was 26. It's just like incredible. He wasn't even employed as a professor, right? He was a second-class patent officer in Bern, and because he did something very stupid, folks. He disagreed with the guy who was going to write his letter of recommendation to get a professor job before he got the job. So don't do that. Don't do that. So he did that to Weber. Weber was the professor and so bad tactics. But, he was right, because he was looking forward way ahead of everybody. And then, as Adam said, 10 years later, he came up, okay, motions are not always at constant speed. They accelerate. And when he realized that, says, but how do I deal with this? And realized that gravity can mimic acceleration. And there was no clear distinction between the two. And that's what we call the principle of equivalence. And you guys all know this because if you're sitting in a car and you accelerate forward, you feel like you're being pushed back, right? And if you didn't know you're in a car, if you're drugged and then woke up and you're in this dark room and you just feel being pulled back, you could in principle say, it's because I have a giant mass behind me that is pulling me gravitationally towards it. and instead it's just the motion of your spaceship or whatever, or car forward. And this similarity between the two, which was the greatest insight that Einstein had, told him that if I want to talk about relativity theory of accelerated motions, which happens to be most motions around, I need to really talk about a new theory of gravity. And then he said, wow, and look at that, I can do that, and you can interpret gravity as the curvature of space. So the more mass you have, the more bent space is going to be. And by the way, time is affected by gravity too, so that the bigger the mass, the slower the clock on top of the mass will tick. So your clock here on Earth and your clock on the surface of the sun will tick separate differently, just because the sun has more mass, more gravity than we do here.
One thing I learned when I wrote my second book was, when we tell the story of Einstein, right, we have this thing that, like, he was not employed when he was not a professor when he was developing the theory. And often what people have this idea is like, oh, he was flipping burgers, right? He's just like, he's working at McDonald's and coming up with relativity. But the cool thing was, no, he was employed at the Swiss Patent Office. And what he was employed doing was coming up with, was evaluating electromechanical patents for time synchronization, right? Because you had these giant factories that covered, 10 miles, and you had to make sure all the clocks had exactly the right, or had exactly the same time on them. So I always thought that was really interesting, that even though, he wasn't working in physics, he was being forced to think about applied time, like this, this new accuracy that was required for the modern age. He was very deeply enmeshed in it. And then the other thing, just about the about accelerations, and a stupid story, but when I was between undergraduate and graduate, I took a year and a half off. And one of the many stupid jobs I had was I was a foot messenger in New York City. So I often had to ride those giant elevators in the giant, in the giant skyscrapers, delivering packages to the financial companies on Wall Street. And I used to carry a little rubber ball with me. And so when you get in the elevator, and when the elevator was accelerating up or decelerating when it was coming to a halt, I try and throw the ball up so that just at the moment it would catch. The ball goes up and it goes down. If you could catch it just when the elevator was accelerating or decelerating, it would look like the ball would just hang in the air for a minute, or the ball would go up, hover for a second, and then go up again. And it was like a variable gravity machine. And of course, everybody thought I was an idiot because I was sitting there with a ball. But it was the coolest thing because, because of that the equivalence of acceleration and gravity, you could make it look in an elevator that was slowing down or speeding up as if the force of gravity was tuning up or tuning down.
In the 1980s, my father lived in Bern. And so I was working in Paris at that time with Francisco Varela. So I would go visit him in Bern a lot. And I would, arrive in the Bern train station and walk up the old town, and there's the clock tower. And, Einstein's patent office was nearby. And it's this amazing feeling when you're walking. It's a beautiful city. And it's this amazing feeling to be walking in a place and thinking, Einstein was here looking at the trains, and, now I'm here. And it's just it's an incredibly moving kind of experience. So,
by the way, you can visit his apartment.
Yeah, that's right.
It's a museum now, and there is this picture, of him with his little baby with Mileva, right, Maric, and him, with the baby, and at the same time a pad of paper in his hand, and one hand with the baby, the other hand calculating. I think that's just iconic. It's just awesome.
Great. So the Bergson-Einstein encounter, or Bergson-Einstein debate, I think it was 1922, I think, in Paris. So the backstory is, of course, that Bergson is Bergson is now in his 60s. Einstein is in his 40s, I guess. So there's a generational difference between them. Bergson is probably one of the most celebrated, renowned philosopher celebrities. Really, he was a kind of celebrity, very well known for his writings in which this idea of duration, the flow of time, and the felt experience of the flow of time, figures centrally in his work and his writings about consciousness and his writings about life. And Einstein is invited to give a presentation on his theory of relativity, which had also, of course, received incredible publicity. And so Einstein was emerging as a celebrity scientist. and they encountered each other in this intellectual event where Bergson said that he came really just to listen, and Einstein gave his presentation. And then, according to the story, the discussion kind of started to flag a bit, and Bergson was invited to say something in response to Einstein's presentation. So the other thing is that Einstein didn't speak French very well, and Bergson was this renowned orator and equally adept in French and English, because Bergson's, I think, mother was English. And so Bergson gets up and, speaks extemporaneously, basically presenting some ideas that were forthcoming in his book called Duration and Simultaneity, which was devoted to thinking about his theory of duration in relation to relativity theory. So he gets up and he presents in this, you can read the transcript of this, and, you can just see that he's this very, adept, articulate speaker. And he basically wants to bring together his thinking about duration with relativity. And so he says that Einstein is to be celebrated in physics and in science for his revolution, and he has no quarrel with any of the scientific findings, but he wants to dig deeper into the philosophical significance of the concepts of time with which Einstein is working. And so he highlights the way that Einstein in his papers defines simultaneity operationally in terms of what Marcella was just describing. A train goes by, so that's a perceptual event or experience that you have that involves passage and flow and duration in terms of lived experience. And you're holding a watch, and you then register that when the train goes by, the second hand is pointing at a particular position on the watch. And Bergson says that that experience of simultaneity would be different if you were a microbe and you were working with a microbial scale event and a microbial clock. That would be sort of that what Einstein considers to be simultaneous in the experiential sense of simultaneity would be this, gigantic non-simultaneity from the microbial position. And so what he's pointing to is there's actually a relativity in experience where, depending on the lived experience and the body and the way that it's, embedded in the world, there's going to be these differences in experience time that are sort of hidden beneath the definitions that Einstein is using to articulate his theory. And Bergson's point, to make a long story short, is really that you can't get rid of lived time or duration as experienced, that will always be present underneath this intellectual architecture that you've developed mathematically. And so it's a point about, the primacy of experience, as we would put it in our book. It's not a criticism of the science. It's an attempt to bring back into view something that the science actually needs in order to be science. Einstein then basically dismisses the point and says there really is no such thing as the time of the philosopher, which is this.
That was the quote, right? That was the quote that sort of like, in some sense, changed everything, ended the relevance of philosophy as philosophy. And now philosophy was going to become subservient to science for the rest.
It's this kind of zinger. There is no time of the philosopher. There's only the time of the physicist and psychological time. So he basically understands Bergson as making a point about, the experience of time, has all sorts of psychological factors that make it be, one way or another, but that's not really relevant to physics. And moreover, though Einstein doesn't really say this, but you could take it as being implied, you can kind of turn around and explain psychological time using the same basic architecture that physics provides. And so Einstein is perceived as you might say, rhetorically prevailing in the debate with this kind of zinger that must have just, chagrined Bergson, because it's basically kind of dismissive and doesn't really come to terms with, the point of his argument. And then subsequently, in Duration and Simultaneity, Bergson has a long discussion of the twin paradox. So this is where you have, you have a twin on Earth and you have a twin in a spaceship. And when they get back together, so the twin spaceship is moving near the speed of light at this, incredibly high velocity. When they rejoin, the clock readings are going to be different. And Bergson tries to dismiss this as a kind of mathematical artifact of the theory, but not as a real lived experiential phenomenon. And there he actually makes a mistake, because there is going to be a physical difference. The experiential difference is more complicated to describe than simply saying they experience different times, because each experiences his own time, and what looks slow and what looks fast depends on the outside perspective. So Bergson, kind of works through this in a very disciplined, rigorous way, because Bergson is actually quite good at mathematics, but he nonetheless makes a mistake, and then he's basically dismissed as not understanding relativity theory. So in our book, we try to, go back to this debate, very much guided by Yamina Canales' wonderful book on the Bergson-Einstein encounter, and really make the point that this is kind of a missed opportunity for actually overcoming the blind spot. And that is realizing that the Einsteinian theory, which is this amazingly powerful, beautiful theory, already is revealing the inadequacies of the classical perspective, but is still not sensitive to its own experiential underpinnings, which Bergson is bringing to light. And so our discussion is, in a way, an attempt to, bring those things together in a harmonious way, where they don't have to be seen oppositionally in the way that they were at the time. And I would say, unfortunately for both the scientific need to retain a connection to its experiential source, and the philosophy, which then was, perceived as not really having a kind of relevance anymore to relativity theory or to physics more generally.
And the consequence is this idea you'll get of like the block universe being ontologically prior, so to speak, right? The block universe is what's really real, and your experience that next Tuesday doesn't, next Tuesday is open-ended, your future is open-ended. That's an illusion, right? And so it's really this beginning in physics of this idea that these formalisms, these abstractions, which are meant to work on a very particular kind of encounter with the world in what we call the workshop, right? The scientific workshop. It's a very organized way of encountering, of getting data and then interpreting data and then using these models to explain the data, which they do amazingly well, that gets substituted for actual experience. And the example here is now the block universe, which is this abstract idea that all time and space already exist. Every event that could ever happen already has happened in this timeless, perfect reality of, Einsteinian the space-time metric. That's more real than your experience of the weirdness of I don't know what's going to happen 20 minutes from now. One gets substituted for the other, and that's why we push on.
Exactly. So I think we have come to our time, as it were, limit for our discussion today. So I want to maybe mention two things as a way of bringing this to a close. One is that The Blind Spot, our book, is now officially out in paperback as of April 1st. So if you've been waiting to get a hard copy of the book, it's now a little bit cheaper in the paperback. And also that the Einstein-Bergson debate I wrote up based on our book for the online magazine Aeon. So maybe we'll have a link to that in the show notes, that there's an article about the Bergson-Einstein debate in Aeon that appeared, I think, last September. And so that gives a very user-friendly, easy introduction into that encounter.
Yeah. And I think I reviewed Jimena's book for Big Think, so I'll also try to dig that out and put in the links.
Great book, The Physicist and the Philosopher, I think it's called.
Yeah, that's right.
Yeah.
Fantastic.
But isn't it true, before we go away, isn't it true that later on in life, Einstein kind of regretted what he said? There's something about him talking about consciousness and realizing how you really couldn't think just like a physicist to figure out what
I think that's right. And I think Yamina may mention that in her book at one point. I think that's right. I mean, this was a, dramatic rhetorical moment. And then later in life, I think both of them reflected on the, way that some aspects of it had not been, were unfortunate. And Einstein, I don't think he ever thought Bergson was right in that sense, but I think he does come to see that the problem of time and flow and consciousness is actually quite deep, very deep.
Right. Because, just throwing this out there, for us, mathematically, if you look at the arrow of the line of time, right, now is a point which has zero duration. But we as humans always talk about the present, and there is a buffer of time, which I think cognitively speaking is about 3 seconds or something like this. There is something
variable. Yeah, it's variable.
It moves, right? It's like a little buffer of time, which go, this is the present. Because in the physics parlance, there is no present, because when you say present, it's gone already. And of course, we function with this idea of the present. So there is something that needs to be worked out.
Yeah, and this is a big theme in Bergson and in William James and also in Husserl, that what we call the present in the sense of the living present contains within it this feeling of something slipping into the past and something opening into the future. So it has a kind of thickness to it that is very different from a mathematical instant or point. Yeah.
And go figure all these things out in the block universe, that yes, at this moment, Marcelo made these crazy things in the hand. It's all in there, folks. Just go look for it.
All right. Well, thank you, everyone. We are going to end the discussion here for today. There is, of course, still more to talk about with time. And next time, we will come at the problem or the issues of time through the perspective of cosmology. And we look forward to joining you again for that discussion.
The beginning and ending of everything.
Right. All right. Bye, everybody.
Bye.